We will now continue our grammar modifications. We just talked about the left factoring, and the goal of left factoring was so we can have one token look ahead. If you have multiple rules starting with the same token, well, that's the common part. Factor it out. So unique rule for each token. That's what we're aiming for. We can just grab a token and know exactly which rule is going to map to, and that's the ideal. Because if we don't have that, then we'll have to deal with it. We'll have to make a choice. If it's a wrong choice, back out, backtrack, and try another choice. If you have unit productions in your grammar, unit productions, they don't really parse tokens immediately. It requires another production. So you're merely jumping to a production and you have to go do another one to actually parse any tokens. The reason unit productions are in the grammar is because they help us to organize and classify what type of thing we're looking at now. For instance, a statement could be a statement, a while statement, a return statement, and then we can go, then those could be the unit productions. Then we'll go to the if statement symbol to try to figure out what's there, or the while, or whatever the type it is. So, but just by themselves, a symbol doesn't actually give me any information. I don't know what tokens they take. So it would be nice if I knew what tokens they take, then I know, first of all, if you have multiple rules that start using the same token, then I will have an opportunity to left factor. Or it just saves a little bit of work if I could just go to a token right away rather than go to a unit production, which doesn't really add any more to the grammar, merely just for organization. So this is an example. I have S going to B. Well, what's B? B is little b, three little b's followed by more b's. So big B is a triplet of little b's. So if I can get rid of that unit production, and here's an algorithm, be careful. S going to AASC, B going to BBBB, don't change. B going to lambda, don't change those. Those are not unit productions. Don't change S into a B or B into a S. Then you're messing up you could mess up your entire grammar and change the original meaning of the grammar. So don't do that. Only thing you're getting rid of is the B, the unit production, S going to B. And how you get rid of that is, well, maybe I'll talk about that. How you get rid of that is just moving B's productions up. So S, instead of going to big B, you make S go to BBB, three little b, big B, or lambda. Since B has two productions, just move it up. In the Lua grammar, we saw, again, these are categories. What are expressions? Well, expressions could be these tokens, or it could be function call. Yeah, function call is an expression, or a prefix expression, or a table constructor. Those are all expressions. I'm just putting them into different categories. But notice there are unit productions. I have no idea what those tokens go, because all I'm seeing is expression going to a function call. Then I have to go look up function call to see what tokens they are. So if we could get rid of these unit productions and expand them, here I'm showing you how to do that. Okay, that makes it a little easier. For instance, a table constructor. Table constructor really is curly bracket, field list optional, closing bracket. Well, just put that in for expression. Instead of another word, another rule, table constructor. Okay, so I'm just insert that right in. Then right away, I know that production, that rule there starts with a bracket. So if I have a bracket, well, it's probably going to map that one. Whereas before, when I had the unit production, I couldn't tell where the brackets go. Is it a function call? Is it a, what is it? I didn't have it. But now I could see right away the bracket rule. And you could end up with, function call, for instance, could also start with a prefix expression. You can see I have 3 prefix expressions. So right there is an opportunity for left factoring. Otherwise, if I have a prefix expression, how would I know which one to go to? Okay, so I should probably left factor. So usually when you remove unit productions, it may uncover these similar tokens or similar symbols that you'll have to left factor. Then finally, I said lambda productions are okay. We don't actually want to remove it. In fact, removing it will actually, it really conflicts with left factoring. When you left factor, sometimes you introduce lambdas. When you remove lambdas, you actually add more rules that start with the same token, which means you have the left factor again. So so we're not going to worry about the lambdas. Your book, most books do talk about lambda production as one of the modifications. Finally, we're going to talk about remove left recursion in the grammar. This is probably the hardest one. So if you look at these 2 grammars, I'm just generating a bunch of A's, nothing else. On one side, I have A, right recursion. On the right-hand side, I have the left recursion. They both generate A's. And the only other production is a lambda. In this case, these 2 grammars are exactly the same. I'll just flip them. So instead of a left recursion, I'll make it a right recursion. First of all, why do we care which one is which? When we're parsing and we're going top down, which means we're going to start with a star symbol, in this case, big A. And then I'm going to have some little a's. I'm going to try to see if they match up, right? Match up to my grammar rules and construct one of these parse trees. If I grab one little a, for the top-down parser, I want to immediately pick a rule, and then that will match that little a and move on. Okay, so it's very much from left to right. As you can see, the tree on the left is sort of left to right. You grab little 1A, you grab another A, and you grab another A. If you don't have any more A's, cap it off, lambda. Very straightforward. You know how to end. You know what to do. As long as there's still little A's, you just keep going. Keep going. The left recursion example, as you can see here, I'm parsing the same 3 A's. But because it's a left recursive, I'm keep going down the tree. At some point, I'm saying, oh, don't go down anymore. That's it. Cap it off with a lambda. And then the A's are just sort of follows as you go back up the tree. Okay, the very first A is actually at the bottom, and the second A is higher, and the third A is way on the top. Okay, so actually, with a left recursion, you will go up the tree. This will be perfect for a bottom-up parser. But for a top-down parser, I want my very first token to be at the top of the tree. And so I go down and parse more and parse more and parse more. So the right recursion grammar is what I'm looking for. The left recursive grammar will not work for a top-down parser. I'll just keep recursing and recursing. I'll never know when to stop because I haven't seen any tokens yet. I'm just looking at big A's and big A's and big A's. But because the only other rule here is the lambda, they're exactly the same. Just flip them. Don't make a left recursive, make a right recursive. That's not always the case. Okay, that's not always the case. Or if you have, instead of a lambda rule, you have a B. Notice now, the left recursive one. Okay, I'm keep going down the tree, big A, going to big A, big A, big A, and then when I'm done, B. Notice, even though B is at the very bottom, it is actually the very first token. You have B, A, right? Even though B is way on the bottom, that is actually the very first token. But the grammar on the left, A goes to A, big A, big A, and or A goes to B, is a top-down parser. So you start with A, and then if you don't need any more A's, you have a B, then you're done. Notice the B on the bottom is actually the very last token because it's top-down. So once you hit the bottom, you're done. But for the left recursive grammar, you hit the bottom and that's your first token. Then your tree starts. B, going back up, A. So it's not the same grammar. If you say, oh, I'm just going to switch the recursion, make it right recursive and left instead of left recursive. Not the same grammar here. B is the very first token. In one, in another one, B is the very last token. So you can't just flip the recursion. How do I do it then? Well, I'm going to follow an algorithm. And you have to follow the algorithm. If you don't follow the algorithm, you're going to get confused. You're not going to get the same thing, right? So take the left recursive example. A goes to big A, little A goes to little b. The very first step I do is identify what the recursive rule is. Well, recursive rule is big A, little a. Big A going to big A. That's the recursive rule. The second rule is fine. Okay, I'm going to change the recursion. I'm going to make it a right recursive because the goal here is I'm going to get a bunch of A's. I'm going to recurse on the little A's. I'm going to keep getting the little A's. I still need the little A's. So I'm still going to keep recursing, except I'm going to do it on the right-hand side. So, but it's no longer A. It changes A, right? Big A. So I'm going to call it a new symbol like X. So X is now going to give me the recursive little A's that I need. So X going to AX. And X has to finish at some point. So I need the lambda. Then I identify all non-recursive rules. In this case, I only have one. Big A going to B. And then remember we said B was actually the very first thing. What comes after B? A bunch of little A's, right? Well, who gives me little A's? The new symbol, X. X gives me the A's. So tag that on. So now I have BX. So the new grammar becomes, sorry, I didn't have it written out loud. So anyway, the new grammar becomes X going to AX, X goes to lambda, and then A goes to BX. That's the new grammar, okay? Oh, I did have that, sorry. So on this slide, so that is the new grammar. So what did I do? Essentially, I rotated a tree. If you remember from your data structures class, this is like rotating a tree. So instead of making B is the first symbol, but instead of making go all the way down to the bottom of the tree, as you saw on the right-hand side, when we change the grammar into a right recursive, we'll actually rotate the tree, making B the first thing you see at the top of the tree. And then you have the A's, A, and then the lambda to cap it off if you don't need any more. So now I have the same grammar. They look different, right? But they're both, the new grammar are both rules are right recursive, no more left recursion, okay? Here's another example. So I have three rules here. One is recursive. The S goes to big S, A, B. S goes to C and D are non-recursive. So what do? Step one, move S to right recursive, but can't call it S anymore. So you got to call it like X or Y or whatever you want to call it. Okay, that's first step. And because X now doesn't terminate, I'll make sure X terminates. So I need to put in a lambda. And the two non-recursive rules, I make it CX and DX because they really start with C or D. And then they have AB, 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 AB after that. Okay. Here's a long, instead of the little a, little b, we're actually looking at a programming language grammar example. Parameter list is ID colon type or parameter list semicolon ID colon type. This is Pascal style for parameter list. Notice the semicolon there is a separator, not a terminator. Again, param list, that's the recursive one. Move it to the end, but give it a new name. So this becomes param list 2, semicolon, ID list, colon type, param list 2. Okay, and then you have to add the lambda, otherwise it never terminates. And then the one that's non-recursive, the ID list, colon type, well, just add param list 2 to it. And this makes sense, right? ID colon type. If you're going to have more, then you're going to have a semicolon, ID list, colon type, semicolon, ID list, colon type, semicolon, keep recursing until I don't need any more, cap it off with a lambda. Okay, so here's another example for removing unit productions. Okay. Here we saw that factor, term goes to factor, is a unit production. So get rid of that. Just put in whatever factor is in for term. Here is a left factor example. I have 3 productions for A that starts with a little a. Well, take it out. Make it AX. What's X? Well, X is what's left on the right-hand side of that blue line. So X is BS, little a, big A, or nothing, lambda. Okay? And the A doesn't need to be left factored, so leave it alone. Here's an example with a programming language grammar, simple expressions. Both these rules start with simple expression, so factor it out. Call it simple expression and then the rest. What's rest? Nothing, lambda, relational operator, simple expression. And then we did this in class, so if you missed class, you're welcome to go through these exercises, and you can always check with me to verify the answers. If you didn't have the answers in class, I won't actually take the time in the video to go through that. So week 4, we're concerned about just getting the grammar. Well, first of all, we need a grammar, which you should already have at this point from homework 2. But once you have a grammar, take a look at those rules. They may not be ready for a top-down parser. For top-down parsers, the number one thing is you cannot have left recursion in the grammar. And if you could get rid of the unit productions, if you left factor everything, will make the parser so much more efficient. But left recursion is a showstopper. If you have a left recursion, you cannot even implement a top-down parser based on grammar alone. So you got to get rid of left recursions before you even talk about it. So week 5, which we'll actually gonna, talk about how to build one of these parsers. The very first one, the recursive descent, and it's based completely on your grammar rules. If your grammar had 25 rules in it, you're going to end up with 25 functions or methods in your program. And those 25 functions or methods will parse whatever tokens you have that match your grammar. Okay, so it's a very easy parser to write, but it can be long depending on how many rules you have. So we'll talk about a very simple algorithm, very simple technique to put it in place, but you still need to start with a grammar. So if your grammar is not ready, you're not going to write a parser. And this is not a reusable parser. It's not going to be, configure so it will parse anything you want. This is going to parse your language, your grammar, very, very specific. If you change your grammar, you have to change the program to reflect that. Okay, so that is what's going to be happening in the next set of lectures. And that was actually given in week 5. And just a reminder that Monday, week 6, February 8th is when our first test, which covers through these grammar modifications.